Hello everyone, welcome again to the next topic in a series of online lectures for ESC190. Before I begin, I just wanted to remind you all that, we do have office hours that are being held online every Monday at the usual time, and we also have practicals, also via BB Collaborate. Um, and yeah, so today's lecture, uh, well, really this week, we're going to be starting uh, a bit of a new set of topics. They're not going to be primarily examinable for you guys, since we do realize, there are extenuating circumstances. So, really just take these topics for your interest. They may show up as, material on the exam for perhaps only bonus marks, but just uh, remember that they're not going to be primarily evaluated. So, so for the next few minutes, just, take some time, to relax, de-stress as you, I guess, listen to my relaxing voice. Okay, so game tree search. Oops, there we go. Okay, so where do we begin? Um, Another name for game tree search is also adversarial search. Basically, what types of search algorithms we did before, they really had to do with an environment that was static. So imagine like breadth first search, depth first search, Dijkstra's algorithm. All of those were also search algorithms, but really they're only dealing with a set of perhaps distances to different communities, different cities, areas on a map that were static. So the distance from one node to another node was always given by, a number. It could be represented by a certain weight in like a graph. And whenever we wanted to search for the optimal path from one location to another, nothing would really change as we were trying to search for that optimal path. So that is what I mean by a static environment. So really the only entity that's really changing our state, as you might want to call it, is you. So when you choose to take um, you know, a certain path from point A to B, you might go from point A to E to C to D, and then finally to B. Um, you're changing the state, and by state I mean your position within that graph. Now, in many real-world problems, um, that's usually not the case. So typically, you're going to have multiple agents. In the first bullet point uh, here, I'm referring to yourself as just one single agent. But typically you might have a bunch of different agents that are interacting with each other in some certain way, and all of them are having some sort of say on what your different state is going to look like. Now, adversarial search is a branch of artificial intelligence and also game theory, where basically, imagine you're an agent that is trying to reach a certain goal, and to reach that goal, you're basically trying to optimize a certain state, but at the same time, there may or may not be other agents who are trying to benefit themselves. So a very typical example would be, a game that you might play. And actually, adversarial problems, they tend to be called games, actually. So something like, like checkers or, the game of chess. You have one player trying to, beat the other by eating up all of their other tokens. Um, and then, if one player or slash agent wins, then by the nature of the game, the other agent will lose. So that's the simplest type of example of an adversarial problem. You have two adversaries who are both trying to optimize their own state. Now, in real-world applications, with like game theory, that's another broad field that, it shows up a lot in economics. So let's suppose you have one business who's trying to choose what is the best price, uh, to have customers buy their products, and but at the same time they know that they have competing businesses who also have the same product, who are also thinking about what should be the best price for them, to choose to advertise to their potential customers. So that's a bit of a more complicated game because, obviously there are a lot of different factors that come into play with choosing the best prices to satisfy your customers. And so, and there's a lot of theory in economics where economists basically try to, treat this whole problem as a very big game with a lot of different factors at play. And, using game theory, they try to come up with the best either price or maybe marketing strategy to really make sure that they will have the best financial outcome. So for this lecture, we're really just going to focus on different types of, simple games. So they're called a zero-sum game. And this is the simplest form of adversarial search. Basically, you have only two agents, so two players, let's say, who are opposing each other, where by definition, by the zero-sum game, basically if one agent were to win, then that immediately implies that the other agent will lose. So the reason why it's called a zero-sum game is that one agent's payoff would basically mean that you have a negative payoff of the same value of the other agent. So hence, if you're to add up all of their, rewards, then they should sum up to zero. So examples of zero-sum games would be games like tic-tac-toe. I mentioned checkers and chess because if one person, for example, like tic-tac-toe, if one person gets a row of X's, then the other person will lose the game. And let's see. So whenever we're talking about, game tree search, so game tree search is like, it's kind of a method, basically, to come up with what is the best strategy for a player in a zero-sum game. So imagine a game consists of a lot of different states, okay? So one state might be for tic-tac-toe, like you might have, three X's, um, or yeah, like two X's at the top or one X at the center, and then you have maybe two O's that are surrounding them, surrounding the X's, for example. That could be like a certain state of the game, and given that, you know, that might tell the player what would be the best move to make. So game tree search is basically a way of trying to encapsulate all the different states that could be in your game and trying to find an objective way to use that information to make the best possible action. So to approach this game tree search, we're going to make use of some terminology here. So the first thing, as I kept on mentioning, is the state. So the current state of the game. So for example, in tic-tac-toe, that could be given by the position of a bunch of X's and O's. There could be three X's, there could be four O's in a certain pattern. For chess, it might be like, you have two knights somewhere, you have a rook that is about it's in the position to eat the other person's, let's say, bishop, and so on. So that's the state of the game, and obviously it's going to change depending on what game you're actually playing. And then there's also actions. So let's suppose you're given a state. Basically, what actions will do, that will return a bunch of different moves that a player can make, given that state S. So, for example, if in tic-tac-toe, you have a certain player, he or she can place an X in one of the empty spots on the board. And each position that he or she can place the X, that would correspond to a different action given that state of the board. Okay, so now given an action that you do, let's say you have an action like A, next state, we're going to use the term next state to denote what is the state that results from applying an action A to a state S. So it's going to result from S after applying an action A. So for example, going back to tic-tac-toe, what would be the resulting, what would the state of the board look like if a player, and I'm going to call him Max, which will make sense a bit later on, if Max places the X at the top part. So maybe if you put at the top, now you're going to have two X's in the top row and one O maybe in the center or something. So that's what next state is. And then there's also something called utility. So utility is where the quantitative metric comes in for how to evaluate how good a state really is. So utility of S, comma P, where P is a term for the player at that certain state. Basically, it's a value that's given to a final state S of the game. So imagine all the different possible ways that you can end tic-tac-toe. So you could have like 3 X's in a row at the top, 3 X's in the second row, 3 X's in the bottom row, and so on. Utility of S will basically give what is the value that represents the outcome of the game. Now this is why I'm talking about a player named Max versus Min. So since this is, all of this is assuming we're playing a zero-sum game, Max is going to try to play the game such that he maximizes the utility. And another player, the second player, which we can call Min, is going to try to minimize that utility. So you can, see based on, their names that each of them is trying to get a completely different outcome. So maybe we can say if Max is the one playing X's, then if you have 3 X's in a row somewhere on the board, that could correspond to a positive value of 1. And if you were to have maybe 3 O's in a row somewhere in the game, the utility of that could be given by -1. So basically, the player Max is trying to play the game such that the game yields a utility that's positive, or basically maximized, and Min is trying to play the game such that the utility is minimized, so something like -1. And, as you're playing the game, typically you want to also have a function that detects whether you're at a terminal state. So is terminal of S, that'll return true if S is a terminal state. So if there's 3 of anything in a row, it could be either an X or an O, then is terminal of S should return true. And this is important so that you know whether it's important to check whether we have an actual valid utility, because the utility function really only applies to a final state S of the game. So we want to first know whether we're in a terminal state before we will check this utility function. So just to warm up with game tree search, I'm going to go over an example of one of the simplest games you can imagine. So we're going to have two players, since that's all we're focusing on for today. Imagine we have a game called the game of 7, and the way the game works is, let's suppose you have each player that starts at a number 0, and the possible actions that they can do, or the possible moves that they can do, is to increase their number by one of 3 values. So it can either be 3, it could be 4, or 5. If one player has 0, that number can then become 3, 4, or 5. And then after that player goes, the second player can then increment his or her number by also 3, 4, or 5. And the aim of the game is basically not to lose. And how do you lose? Well, if you ever reach a number of, let's say, 7, because I'm just going to call it the game of 7, the more general game that this is derived from, by the way, is called NIM. And I believe that uses the number of 21, but I'm going to use a very small number, as you're going to see very soon why. So basically, the first player to reach or exceed 7 will lose. And let's assume that the two players' names are Max and Min. They're playing against each other. And let's say we get a utility of 1 if Max wins, and a utility of -1 if Min wins. Okay? All right. So as I've been saying all along, this is called game tree search. And now you're going to see why this corresponds to a game. Or, sorry, to a tree. So a game tree. So let's start off with this terminology here, with how these diagrams are on the board. So I'm going to denote by a triangle, an upwards facing red triangle as player Max. And over here, this is going to be the root of my tree. So this is the initial state, and I'm going to denote by these numbers as the player's current sum. So they're both going to start off at 0, so I'm going to have a state that's just 0, 0. So that means Max has a count of X, Min has a count of Y. Now, to make use of this tree, we're going to think about what are the next possible states. So it's Max's turn, and he goes, or he or she goes. And he either adds 3, or he adds 4, or he adds 5. So basically the next state would be either here, here, or here, with 5, 0. Okay? So 3, 0, 4, 0, 5, 0. So that's great. You can go one more level. For each of these states, the next ones are where player 2 will add, or player Min will add either 3, 4, or 5 over here. Okay, and the same thing goes for the rest of these games, or these little plays that we do here. So 3, 3, 3, 4, 3, 5, 4, 3, 4, 4, 4, 5, 5, 3, 5, 4, 5, 5. None of these are terminal states yet, because neither of the players has reached a sum of 7 or more. And I think you're starting to now see how big a game tree can actually get, depending on how complex your game is. So you keep going. Okay, so we go another level for each of these, and now you can start to see that we have reached a few terminal states. So for example here, from 3, 3, if player 1 was to add 4, he would get a 7, and that would basically denote an end of the game. So player 1 has a 7, and that means that, well, player min wins, right? You can have 7-3, you could have added 4, or sorry, 5, so you get 8-3, and or if you could have also added just the 3, so that you're not at a terminal state yet. The same thing applies for the rest of these levels, and you can see by green I'm denoting a terminal state. And these numbers that you can see are just the utility values. So since in here player max reached a value of 7, that means that this corresponds to a -1 because player min has indeed won the game. Now there are a few other levels. Keep going. Um, you can see that they're all going to be concentrated to the left because all these nodes in the tree are already terminal states, so it doesn't make sense to try to, expand on them. So these are more states, and you can see we still have 6-6 here. We go one more, and yeah, now you can see we've fully expanded our game tree. So these are all the possible states. All the leaves of the game tree denote all the terminal states of our game. Now, even with such a simple game of 7, I specifically picked 7 so that I could actually draw the tree on the screen. But, other games, almost every other game you can imagine, even just tic-tac-toe, uh, it won't be possible to draw the entire tree. Because there's just so many different possible ways, so many possible different configurations you can put the X's and the O's, and yeah, every game, it's it's basically you're gonna have to try to imagine what the game tree looks like. But this simple game was just here to kind of show you what a very, very, very simple game tree would look like. Okay, so now, so that's great. So this kind of shows the structure of what a game tree is, but how can this actually be useful is the question that we should be asking here. Um, and specifically, I'm talking about how should we optimally decide what move should, let's say, player max make in order to get the best possible result. So this is where an algorithm called the Minimax strategy comes into play. Okay, so basically Minimax, we're going to define the Minimax value of each tree node. So imagine each of these triangles is another node. We're going to define a different Minimax value for each of them. So remember, for a terminal node, each of these green nodes here are terminal. They have a certain value. What the Minimax tries to do is to also provide a value for the non-terminal nodes as well. Because you can imagine if we knew the values, you know, the values of each of these nodes, that would, that would inform, let's suppose we're up here, we haven't, maybe explored all of these nodes yet. Imagine player max being up here, choosing what action to make. If you could have some information about what are the possible, what would be the utility, that would result if you were to choose this move, that would inform him of which move he should make. So for the max node, basically the minimax value will be the maximum of its children's minimax values. And the min node, well, its minimax value would be the minimum of the children's minimax values. So the goal is to assign minimax values to every single node until the root, which corresponds to our current state of the game, till the root knows what would be the best play to make. Okay, so let's just go over it, in some more detail. This is the pseudocode for doing the minimax strategy. Basically, what we do is we try to apply the minimax function onto, your root. So let's suppose I start my game, I'm player max, and I know that I have 0, 0. That's just the initial state. Okay, so the trick here is to consider a move. Okay, so in this function, I am going to call maybe get min on the next state of s, which is 0, 0, comma a, and that a would be add 3. Okay, so I'm going to call get min on the next state, which is 3, 0. So that's why I'm calling get min here. And then you kind of you keep going down the tree. So I call get min, but if you look at my get min function, what I do is I am going to try to find the minimum of all of its children. And to find the minimum of all its children, I need to therefore get the value of everything below me, or everything below min, which is just going to be a few max nodes. So I get the max of the next state again, so 3, 3. And then I just keep on going down the tree. So I'm basically exploring. I keep going and going until I reach a terminal state. So I called get min, then I called get max, get min, get max, get min. And if you look at the code, how we program it is in get min, I'm always going to check if I'm at a terminal state. So that's where that isTerminal function comes in handy. And you're going to notice that 9.6, that indeed corresponds to a terminal state, right? Because 9, one of the numbers is greater than or equal to 7. So I'm going to just return, from this getMin function, I'm going to return the utility of s, which is -1, right? Because this corresponds to max getting 7 or larger, which means that min is going to then win. And after I return out, and remember, all of this corresponds to, a recursive, call stack here. As soon as I return out, I'm going to go back up a level in the getMax function. So getMax. And what am I going to set max to? I'm going to set that equal to the maximum value of, my current value, which is now -1, and the rest of its children. So that's why I'm doing, for A in actions. And, I kind of skipped a few steps, but as you explore the rest of this node's children, you might get this and this. They all have to be -1. And now the minimax value, so the minimax value of max is going to be the maximum of all of its children. So the max of -1, -1, -1 is going to be -1 as well. Okay? Now I just continue. So I get the children of min. So you can see here that it has +1 and +1 as well. And what is min going to choose? Well, its minimax value is going to be the minimum of all of the children, which you can see is happening in the getMin function that's called on this node. So it's going to be the minimum of all the different values, and eventually, as it exhausts all of its children as such, it'll get the minimum of -1, 1, 1, which will be just -1. Then we just continue that, so max will get the maximum of all of its children, which will be -1 as well. And then we continue again for this. So I skipped a bunch of steps. It's basically the exact same thing as I did before. Basically you're just trickling on up all of these values, all of these values to get the minimax values. And you can see all the resulting minimax values, -1, -1, and because all of them are the same, min is just going to get -1 because that's the minimum of all these 3 -1s, and so on. So after you complete that entire process, so what we did was we got really all the terminal value, the utility values, and we just kind of propagated them all up Eventually, we're going to get all the information that we need, all of these minimax values, and it goes up to the root. So basically, what happened in this case? Well, unfortunately, the minimax value of max is over here at the root is -1. And what that basically means is that no matter what max will do, if he assumes that min will always play optimally, that means that he's always going to result in a negative value, which basically means, in other words, that this game is actually rigged, and no matter what, Max unfortunately is going to lose because the best possible value that you can hope for is a -1. Okay, so if both players play optimally, he will get a -1, and he'll result in one of these states that corresponds to a -1, also known as a loss for Max and a win for Min. So basically this is showing that whoever starts the game is almost certainly going to lose, unless Min decides to play very, very suboptimally. Okay? Now you might be wondering, okay, well, if Minimax just assumes that both players play optimally, then how do you know that, your method will actually work? And I'm not going to show it, but you can actually, for zero-sum games in particular, you can actually prove that if you were to play your strategy, given the minimax uh, theorem, then you are basically guaranteed to do at least as well um, as your minimax utility is, your minimax value is. So you may perform as well as your minimax value. You may even perform better if min decides to not play optimally, but you will get basically, a lower bound is represented by your minimax value. Now, what is the time complexity of minimax? Well, if you were to basically go through this entire algorithm, your time complexity would just be how many of these nodes are there in this tree, because all of them correspond to a different node that we had to explore. So if we say that B is our branching factor, which is basically the number of nodes that can be the children of a given node. Um, so that corresponds to the different types of moves you can do. You can either add 3, 4, or 5. Then B would be equal to 3. So that's the branching factor. And if we call D the depth of the entire tree, so, for example, here it would be 1, 2, 3, 4, 5. We would have a D equal to 5. Then the time complexity would just be given by an upper bound of O of B to the D, which would be 3 to the 5. So that basically gives an upper bound for how many nodes are going to be in this tree. And the space complexity, well, since we're doing a lot of recursion, our space complexity is just going to be given by the depth of the function call stack. So when we recursively call our getMin or getMax, like when we're at minimax, we call getMin. At getMin, we call getMax, and then at getMax, we call getMin. At getMin, we call getMax, and so on. That's all adding overhead to the function call stack. So yeah, basically that'll give you the space complexity is just going to be O of D, so the depth of your tree. Okay, and that was basically an introduction to, Minimax. And now you might be wondering, well, okay, it seems Minimax will always be guaranteed to give you the, basically the optimal action that you should perform, right? Unfortunately, in this case that we have here, the optimal move that Max can make will still result in his loss, but that's just because of the nature of the game. If you were to choose a different game, I can assure you that you could have a lot of more interesting results. But no matter what, in Minimax, you're always going to explore the entire tree. Now, if you remember, I said that with games, you know, typically you're going to get a tree that is much larger than this and frankly a lot more difficult to actually even imagine. So, so Minimax is nice in that it can give you an optimal, you know, path to take, um, but it's not very practical because, computers are limited in resources. They're not going to have all the time in the world, like O of B to the D, which can, as you can see, it's exponential. It can get extremely large. As an example, chess has a B value of around 35. And, typically if, players play like 50 turns or something, you're going to get, um, you know, a time complexity of 35 to the 50, which, that's almost an uncountable number, you know, in the practical sense here. So that's why chess is a very hard game to solve, and it's just infeasible to create the entire tree. Now, one way to avert this is to use a method called alpha beta pruning. So in more complicated games, searching the entire tree, and assigning min-max values as such to every single node, that's just not practical. And it can take an extremely and, you know, a prohibitively long amount of time. Now, alpha beta pruning gives you a way to not always have to explore the entire tree. So what I mean is that, as you're exploring the tree, you might find that given the state, maybe not the best word to use, but given the state of your search that you're in your game tree search, you might actually find that you don't actually have to keep on exploring the rest of the sibling nodes. And the way that we're going to do this is we're going to make use of an alpha and a beta value. And how we're going to define them is that alpha will represent the maximum of all of its previous siblings' minimax values that have been seen so far. Another word would be that it's the highest value seen so far by the max player. Beta will represent the minimum of its previous siblings' minimax values seen so far. In other words, it will be the lowest value seen so far by min. So to show this in a diagram and to see both alpha versus beta pruning, let's suppose, let's look at the left part of the screen first. So, let's suppose we're in this part of our search. We have a lot more interesting values. We found, this minimax value is 3. This max's minimax value is 5, and so on. And let's suppose we're now expanding this max node over here. And so basically beta, in this case, would be equal to 2 because, this is the best possible value that min has seen so far. It saw 3, it saw then 5. Well, since 3 is still smaller than 5, you know that min is going to take the 3 anyway. It then reaches a 2. Well, hey, 2 is even smaller than 3, so yeah, beta is equal to 2 now for this part of the search. So beta equals 2 corresponds to this 2 over here. Now, if we start expanding, the children of this node, we see 0. Okay, it has a value of 0. That's great. What else do we got? Well, the next child has a value of -1. Well, since this is a max node, I don't really care about the -1. I couldn't care less about anything, really beneath it, because I know I'm going to take 0 over -1, because 0 is larger than -1. It then reaches 2 as the next contender, And well, now we have seen an example where we can actually start pruning. And why is that? Well, 2 is now our next local really maximum that the orange max node has seen. So 2, so whatever value, minimax value that the orange node takes, you know it's going to be at least as large as 2, right? Because it's a max and wants to maximize its minimax value. Now, given that, if this becomes a 2 or more, does it make sense to even consider this node? And the answer is no, because we have been keeping track of beta equals 2 this entire time. Now, since min up here is always going to try to minimize its minimax value, you know that it's going to get a 2 or smaller. If this guy is a 2, well, it doesn't even make sense to consider anything else that has to do with this node. Because since now we know that this value is going to be at least 2, it could be a 2, it could be a 3 or a 4, that doesn't matter anymore because this min is going to, it's already seen a 2 and it's only going to get a 2 or smaller than that, out of all the possible children that it can explore. So basically that tells you that we're going to prune, anything else in the children of this orange node. So that's what I'm denoting by this red cross here. Okay, so that's an example of alpha pruning. Okay, and beta pruning is kind of similar. Basically, let's suppose we're given these minimax values, and we've reached this state, and min is considering a bunch of different options, and so far its largest sibling has a value of 5. So right over here is 5. And that means that max up here is definitely going to take a value of 5 or higher. Well, if we look at, this part of the search, we see that it has a value of 6, okay. And then the next child has a value of 4. Well, because this has a value of 4, we know that min is going to have a value that is, less than or equal to 4, because it's only going to get the minimum possible value of its children. And if this is going to be less than or equal to 4, and we know that max wants a value of 5 or larger, and it already has that option, it no longer makes sense to keep on exploring the children of the green min node over here, right? Because it could have a value of 4, it could have a value of 3 or 2, but no matter what, max is definitely going to reject whatever min can produce for it, okay? So therefore we can prune, and this is called a beta prune. It'll prune all of the rest of the siblings here. Okay? So you can see alpha beta pruning is basically going to allow us to basically kind of reduce the search size of our entire game tree search by just forgetting about parts of the tree. So the way that alpha beta, the pseudocode will work is that it's very similar to Minimax, except we also add a few different conditions. We're going to check whether a value is larger than or equal to beta, or a value is smaller than or equal to our current alpha value, and that'll basically tell us that if a condition arises where we should prune, then we just return early on. So that's equivalent to pruning the rest of what we could have explored in the tree. Okay. So here's an example that I want to show you with alpha beta pruning. Imagine we have a tree like this, and we're given a bunch of terminal states. I made them a little bit more interesting than what we saw in the game of 7. And now what we want to do, imagine we're player max up here, and we want to determine what is the best move to make. Should I go this way, or should I go this way in my tree? So I'm going to call my function minimax alpha beta on this state up here. Okay? So I'm going to keep track of a bunch of three different values, really. The value, so what is the current possible minimax contender, and also what is going to be the alpha and the current beta value of the node. Okay, so if I keep on going, I'm just going to initialize this max. I'm going to initialize its value to negative infinity so that it's very easy for me to get the first value here, because basically I'm going to see whether it has some finite value. I'm going to get the maximum between negative infinity and the value, and the value is always going to win, and so on. So I'm just going to basically get the max of all of my children here. So if I continue, now I'm going to iterate through all the different possible states after this max state here. I'm going to call getMin. I'm going to do a similar thing where I initialize its value to positive infinity instead, just so that it's easier to get the minimum of positive infinity, this value, and this value. I then go another recursive step. I call getMax. Again, initialize to negative infinity, and so on. And now I reach a terminal state, which is 6 over here. That's the utility that I have. I'm going to detect that it is indeed a terminal state, so I'm going to just return out. And now, after I do that, I come up one level from the recursion. I set val equal to the minimum between 6 and that used to be positive infinity, so the minimum value will be 6. And now my current contender for my minimax value of this node over here is going to be 6. Now I continue with the added step with alpha beta pruning, in that I set a beta value equal to the minimum of beta and value, where I initialize beta to just positive infinity. And remember, beta is the best value that min has seen so far. So that's just going to be 6. And then, I basically continue in this fashion. I look for the different possible states. I notice 10. That's not large. That's not smaller than my best value of 6, though, so I'm just going to ignore it. And then, since I've explored all of its children, I return out, and I'm going to return 6. So this is my final minimax value on this node over here. Afterwards, I'm done with this child. I go up another recursion, and this node has another contender of 6, because it's the only child that Max has explored so far. And then I set its alpha value equal accordingly. So it's the best possible value, which is basically the maximum possible value that it's seen so far. So I set my alpha equal to 6 here. I then go down another level. And now remember, what I'm doing is, because I've already gained some alpha beta information here, i.e. this alpha, I'm going to pass it down when I call my function next. So when I called this part here, this getMin, that's why I'm in the getMin function, notice how I passed in this alpha and beta value, and in this case it was 6 and positive infinity. I passed that in so that when I'm in here, I can now know, what is the best value seen so far by Max. So I'm basically remembering that it's 6, right? This guy has a value of 6, and I've seen, well, I'm going to make use of that information to know whether I should prune at all. So I'm going to explore the child of this node here. I'm going to notice it's 4, and that's better than positive infinity for sure. 4 is definitely smaller than that. And I update the value. Now here is where we have our first example of a beta prune. Okay, so now if you look, this guy, this min just found a value of 4. Now, does it make sense to explore any more of the children of this node? And the answer is no, because my alpha value is 6. So we know that max over here is definitely going to take a value of 6 or higher. But this min over here, it's going to take a value of 4 or smaller. So therefore, it doesn't make sense at all to keep exploring the children of this min node. It's going to be 4 or less, but max already has a much better option. It objectively has an option that's better because it has a value that's 6, which is higher than 4. So hence, we're going to skip exploring this child, which has 9. I don't even care what this value is. We're never going to find out in our game tree. And we're just going to return out early. We're going to go back up, to here, and we're going to return 6. Okay, because it doesn't make sense to explore anything about this child here. It's pretty much, it's dead to the parent here. Okay. Next, we go up. We have 6. We update the value of min, 6 now, because it's basically just getting the only minimax value that it's seen so far in its only child that we explored. And it's going to update its beta value accordingly because, that's the best value that min has seen is now 6. We're going to pass down our alpha beta to this child here, negative infinity, negative infinity 6. And we keep going. We're going to go down again, past its alpha beta values, and explore 14. I'm going to update that value accordingly. I'm going to update beta, but we don't really have to because 6 is smaller than 14. And then we explore the next child, which is 2, and this time we are going to update beta because we now found an even better value for the min, which is 2. And then now we're done. We return 2 as the final minimax value of this min. We keep going. The value of max, its next contender, went from negative infinity to 2 because its only child has a minimax value of 2, so it's going to become 2 over here. We next update its alpha value because now alpha has now, we found another best value that was seen by max so far. So we update alpha from negative infinity to 2. We then pass that all down again to the next child. We get a 20 here because it only has one child in this case. We update the beta accordingly, which, that doesn't really happen because 6 is still smaller than 20. So return that. And now let's think about what is going to happen here. So we just found out that this min has a value of 20. And this max over here, it wants to, well, maximize its value. So what's going to happen is it's going to update its value to 20, right? Because that's the maximum of 2 and 20 is just going to be 20. But do we really need to explore any of the nodes that are down here now? And, well, the answer is going to be no, because given, the beta value that we have, which is 6, because 20 is greater than or equal to 6, that shows that really there's no way that our min up here is ever going to choose this max to be its child, or it's never going to inherit its minimax value up here because its best value that it found is 6, right? That's why it was so important to pass down our updated alpha and beta values. So min over here, it already has a good option of 6. And if this guy has a 20, well, no matter what we choose, no matter how we explore this part of the tree, well, it could be a 5, it could be a 25. No matter what, this max value is going to be greater than or equal to 20. And because of that, there's no way it makes sense for min to even consider anything that has to do with this node here. So we can just stop. We can return early. We can return the value. And basically, this is our example of alpha pruning. So we're going to return out early. And, we keep going in our min function. We're going to return 6 because it has no more children to explore. And we finally finished this part of the tree. We then update the roots value accordingly. Its only child it's seen so far has a minimax value of 6. We update alpha accordingly, because that's the best possible value that max has seen so far. We then pass down its alpha and beta values down to its child, and we then reach the first child here. It has a terminal. It's an early terminal state, but still a valid state anyway. It has a value of 5. We update its minimax contender for this min to 5. And now, notice what happened over here. Well, since this has a value of 5 or less, because it's min, it doesn't make sense anymore for max to even consider anything that has to do with this child over here, because it already has a best value of 6. So it's alpha value of 6, which we have passed down here so that we can do our check. And since you know that max is going to get a value of at least 6, therefore it doesn't make sense to even consider a value that's 5 or less. This could be 5. If we were to explore all of this, maybe we would have gotten, maybe a 3 or, a 2 or whatever. And, no matter what, it's not going to be larger than 6. So hence max is just not even going to consider anything that has to do with min over here. So hence, you can see we just pruned a very, very large portion of the tree. Okay, so we update the value accordingly. We're going to return, val, because now we're done. And now we have basically finished our search given this node as the starting state. So now we're done. And the next part of the Minimax alpha beta algorithm is to go through all the different states and choose the one that actually corresponds to its Minimax value. So this move over here, this left move here corresponds to a minimax value of 6, so hence it should take that move. And you can see how the game is going to play out. So this will become this. Min will then choose the action to minimize, so that's 6, so it's going to also go to the left. Max will also try to maximize. And it has a value of 6, so it will go down the left again. This guy has a value of 6, so it's going to try to minimize, and it's going to choose this terminal state down over here. So this is going to be our final state if both of these players play optimally. Okay, so you can see here that we trimmed off a pretty good chunk of the tree. And alpha beta pruning is great in the sense that on average, it can actually reduce the tree size by a factor of 2. So that's kind of like effectively the branch factor becomes the square root of itself. So perhaps in chess, it would go from a value of 35 to a value just under 6. So already you can see that we're making a major improvement with alpha beta pruning. Now, even given that with alpha beta pruning, it's great that we've reduced how much of the tree we need to explore. You know, a lot of games, even chess included, are still complex enough that it's still not really feasible to just throw alpha beta pruning and just hope for the best. Because no matter what, with alpha beta pruning, you'll notice that we still had to explore at least all the way to the depth of the tree, at least for one of these branches here. We still have to go all the way to the bottom depth. And unfortunately, with a game like maybe like chess, which could have like 50 moves, that could still not be very practical. So what typically gets done is, there's something called an evaluation function. And evaluation functions are basically like a heuristic approach, which means that we try to give an estimate for what would be the corresponding minimax value of a node, but without having to traverse all of its children. So let's suppose, maybe we're up here, and we don't really want to explore all the way down to the bottom. An evaluation function will try to give some sort of, educated guess for what the minimax value is going to be. So obviously, if you were to only use evaluation functions, that no longer guarantees that the move you make will be optimal because now you're making an estimate. So you're kind of trading off time for you know optimality of your solution. But a lot of the times, if you can come up with a very good evaluation function, for chess, that might have to do with the configuration of the board. So like how many pawns did I capture? Where are the rooks or queens on the given board? Am I like, does the opponent have very little pieces? Do I have very many? Um, that would all correspond to a higher value of the evaluation function and the opposite for the other player. Another way, another strategy that you can make with game tree search is just limit how deep you go into the tree. So like if you have, if I'm up here and I'm like, okay, I don't really want to go more than like five depths or five plies is kind of like the jargon. Let's suppose I want to limit the depth to five. I might have like a global variable that keeps track of, oh, I went over five. Well, okay, no matter what, I'm just gonna go with whatever minimax value I have so far. So that's called depth limited search, where you just cut off the search at a specified depth of your call stack. And the final way that, well, of course, not the final way, of course, there are many, many ways to employ game tree search while saving resources. Another way is to use a lookup table. So, and this mostly pertains to initial moves. So let's suppose you're in the game of chess. There's a bunch of different opening moves that you can make. Um, I think one is called like Fool's Check or Fool's Mate or something. There are a lot of different opening moves you can make that, over the years, humans have, they've kind of tabulated all and documented all the different like optimal moves that you can make at the very beginning of a game. So imagine if a computer can store in a lookup table what are the best initial moves to make. That could save a lot of time than just searching a huge game tree to find the optimal move. So lookup tables, as you're going to see in the next lecture actually, uh, sometimes if you tabulate um, possible, moves you can make, that can help a lot in saving time, uh, which would be wasted with searching through a very large tree. Okay? And another thing I kind of forgot to mention with alpha beta pruning is that even though it's also a great, algorithm, at the beginning, It can also depend on the order of moves that you make. So let's suppose I was unlucky enough to choose a certain move that would not have uh, given me enough information to prune the tree, then I might be unlucky enough to actually end up exploring a majority of the tree instead of pruning as early as I could. Okay? Anyway, so that's basically all I wanted to say with game tree search. Remember, it's not going to be primarily evaluated on your tests that might be coming up. But if you're interested and you want to explore more into the subject, I would recommend trying to practice actually coding up the Minimax algorithm first. So let's say maybe for the game of 7, and how about we change that 7 value to n, where n is some sort of parameter. If you want to implement the game of nim, for example, you would change n to 21. Um, and yeah, try to implement Minimax in Python. Python is usually, the easiest to implement, more complicated algorithms that we'll be looking over this week. And also try to modify your above algorithm such that it actually employs alpha beta pruning. So I'd recommend, maybe making a class for your game and making a few different methods that implement like, minimax, another method for getmax, and another method for getmin. And, you can try to even compare, if you increase n, you can imagine how big the game tree will be. Try to see maybe, you know, how much time might get saved if you were to use alpha beta pruning versus just the vanilla Minimax algorithm. Okay? So that'll be your exercise for this lecture. And of course, with all exercises, we'll try to post a solution sometime in the near future. Okay? All right, and that's pretty much it. In the next lecture, we will move on to dynamic programming. Okay, have a good day.